So this is lab 3, and in this lab, we are finding the unknown mass of a black hole by analyzing the motion of a revolving star. So how do we find the motion? We can look at CSV data given by scientists, which observes the x and y position of a star over a certain number of Earth days, with the data changing every Earth day. And we can take the CSV data and put it into Python with some physics conditions, and we can output a model of the star's motion and find the unknown mass of the black hole. And we found the unknown mass to be 4.35 times 10 to the 31 kilograms, with hardly any deviation throughout the motion of the star. And this was also consistent with what is required in WebAssign, so it is accurate and precise. Physics concepts: the star is the system, of course, we're associating with. It's orbiting in an ellipse, as most things do orbiting around gravity. F net is not equal to 0, it is equal to the change in momentum over time, because m times the change in v over change in t is equal to mass times acceleration, which is equal to the sum of the forces by Newton's second law. dp dt itself can be broken up into two components: dp dt parallel, which is associated with the change in magnitude of the momentum, and dp dt perpendicular, which is associated with the change in direction of the momentum. Elliptical motion implies both components are present, meaning one's not 0, because with a circular orbit, the only thing that's changing is direction, but the elliptical motion is not just constantly changing direction, it also implies a change in magnitude around a certain object. Forces to consider: we only have one force to really consider, and that's the force of gravity due to the black hole, which is equal to the gravity equation, g being the gravitational constant, big M being what we need to find, little m being the mass of the star, and d being the distance between the star and the black hole. The mass of the star is 4.94 times 10 to the 27 kilograms. Change in time has already been discussed, and we have the position of the black hole, which is specified as h in the code, and here are some of the CSV data. So using basically an index, we can find the initial and final velocity, find the change of velocity, multiply this by the mass, and we can find delta p, which is the change of momentum, which we'll need for this. And we can divide that by the change in time to find dp dt, and that's equal to the F net, of course, by Newton's second law, as we discussed. We can find dp dt parallel, which is equal to the magnitude of dp dt times p hat, because dp dt parallel is parallel to the motion of the star. This is equal to F net parallel by Newton's second law. dp dt perpendicular is equal to dp dt minus dp dt parallel, because the two components add up to make dp dt. And F net perpendicular is equal to dp dt perpendicular by Newton's second law again. And we have the model. The black arrow represents F net parallel, blue arrow represents F net perpendicular, and the yellow represents the total F net, which is pointing in the logical direction, which would be towards the black hole, which is present in the middle of the star's motion. And we have to adjust the arrow scale to be very, very small, because how long the arrow is in meters corresponds to each Newton of force. So we have to make it like basically 0.00 something, or 0.000, like 23 meters to a force, because the force is so big in this case for gravity. And since the only force acting on the system is black hole's gravity, that force is F net, we can use the gravity equation here to find m, and this is printed on the Python shell, and the deviation for this mass was 0.08%. So that's really good. So it's very consistent data for the mass. So what does it mean? How are F net parallel, and F net perpendicular different from dp dt, dp dt parallel, and dp dt perpendicular? Well, FNet and its components measure the sum of forces acting on a system in a particular manner. So it's basically just associated with the forces itself. dPdt is the exact same value. I mean, it's the same thing. They're equal to each other, but it has to do with the change in momentum over time. So dPdt parallel and dPdt perpendicular are just associated, again, as well, with the change in momentum in a certain manner. So if a new black hole was placed in place of the old one with the same star position data, could you tell the difference in the two masses if a difference was present? No, because you're putting in the exact same data. I mean, so everything is exactly the same. You're running the exact same lab again, and you shouldn't expect a different mass. It doesn't matter because the data of the star is a dependent variable. The black hole itself is not. And so that is it for my lab.